Hello friends. So today we are going to discuss a few questions from the year 2004. So from the 2004 year we are having total number of six questions. And the first question from the year 2004, it says that a point object is placed at the center of a glass sphere of radius 6 centimeter, refractive index 1.5. The distance of the virtual image from the surface of the sphere is. In this case, we are given a glass sphere. So we can draw an approximate figure for that. So it is something like this. And we have a center and the object is placed at the center. Okay, so here lies the object and radius of this sphere is given as 6 centimeter. So we have to find out the image which it says in the question is a virtual one. Okay. So and the refractive index of glass is also given, that is 1.5. So we can say that for air refractive index will be 1 and for the glass, that is N2, it will be 1.5. Okay. And we can just use the formula which states that we have N2 upon V minus N1 upon U is equal to N2 minus N1 upon R. And radius of curvature is given to us. So we substitute the values here. Okay. We get this as 1 upon V minus 1.5 divided by U. And this will be minus. And let me correct. So here this should be our N1 and this should be our N2. Okay, now it's correct. Is equal to, we have 1 minus 1.5 divided by, it is given as minus of 6. And this will be our positive. So therefore, we can write that our image, the object is also at a distance of 6 centimeter, that is minus 6. Now it's the correct one. We substitute the values. We can write it as 1 upon V plus 1.5 divided by 6 is equal to minus 0.5 divided by minus of 6. So this gives that the V will be equal to minus 6 centimeters. So this is our answer. Virtual is that our 6 centimeter. Option number C is correct. Option C is correct. Next question. It says that in a YDSE bichromatic light of wavelength 400 nanometer and 560 nanometer are used. The distance between the slits is 0.1 millimeter and the distance between the plane of slit and the screen is 1 meter. The minimum distance between the two successive regions of complete darkness is. So we have to find out the distance between two successful, you can say darkness, or we can say the successive where they are going to provide a destructive interference. Okay, so we have to find out that. And basically we have to find out value of N and M. Okay, and we are given that we have two wavelengths, and we know the standard formula is our for a minima, we have that our y is equal to 2n minus 1 divided by 2d and multiply by capital D. Now we have two wavelengths. Let us call that lambda 1 as the first wavelength, which is our 400 nanometer, and second wavelength, let us suppose that is lambda 2, and we call this for as 560 nanometer. And the first wavelength, we assume that the first wavelength, this coincide with nth minima, and the second wavelength coincides with the mth minima. So we can remodify the given equation. Let us call this as equation 1. So we can say from equation 1, we can write it as 2n minus 1 lambda 1 d upon 2d is equal to 2 times m minus 1, and this gives us lambda 2 d upon 2d. And here this d 2d cancels out, and this gives us that 2n minus 1 lambda 1 will be equal to 2m minus 1 lambda 2, and we find out the ratio of 2n minus 1 and 2m minus 1, and this comes as 14 by 10, or we can also write it as 7 by 5. Now we have to find out the different value of n for which they maintain this particular ratio, but the value of n and m we know are integers, or mean valid integers rather. So first of all, let's try that our 2n minus 1, which is equal to 7, and this gives us that 2m minus 1 is equal to 5. And from here we can say that the value of n is equal to 4 and value of m is equal to 3. So this is one of the valid integer. Second, we do it for the ratio, so we can write this as 2n minus 1 is our 14 and 2m minus 1 is equal to our 10, and this gives us that our n is equal to 7.5 and our m comes as 5.5. So this is not a valid one. Similarly, we expand this ratio, and now we solve it for 2n minus 1 is equal to 21 and 2m minus 1, this gives us 15. So from here we get our n will be equal to 11 and our m will be equal to 8, and this is also our valid. Okay. So basically it means that for the first valid value, that n is equal to 4 and m is equal to 3, we can write that coincidence happens at, we have fourth minima, for the wavelength of 400 nanometer, and third minima for 560 nanometer. Similarly, we can write for the second value one, that is the 11th minima for 400 nanometer and 8th minima for 560 nanometer. So these are the two coincidence is going to happen for these two values. We can find out any number of values, that doesn't matter, but here we are mainly interested in two parts. So therefore we can write it as, next comes the calculation of the location of coincidences, that is value of y. Calculation of location of coincidences. And we use the standard formula, that of the y is equal to 2n minus 1, and we have lambda 1 d divided by 2d. The first coincidence, and this happens for value of n is equal to 4. So we can write that our y of 1 will be equal to 2.4 minus 1, and this is our 400 nanometer minus 9, capital D is given as 1, and small d is our 0.1 into millimeter, that is 10 to the power minus 3. So this gives us 14 millimeter. And the second coincidence occur for value of n is equal to 11. Second coincidence is for value of n is equal to 11. So we get our y of 2 will be equal to 2 multiplied by 11 minus 1, and rest of the things will be as it is, 10 to the power minus 9, 1, and this is 2 into 0.1 into 10 to the power minus 3. So we get y2 will be equal to 42 millimeter. And then we are going to find out the distance between two successive coincidences. Distance between two successive coincidences let us suppose that is our delta y, y2 minus y1. So we get a 42 minus 14. So this gives us delta y will be equal to 28 millimeter. So option number D is the correct one. Option D is correct. We go to the next question, and it states that white light is incident on the interface of glass and air as shown in the figure. If green light is just totally internally reflected, then the emerging ray in the air contains. So it means only the light green is being totally internally reflected. So it means the incident angle is equal to the critical angle for the green. So you can say that our green light is total internal reflection. So therefore we can say that incident angle and this intersect angle is at this particular point. Let us call this as P. So incident angle at P is equal to critical angle for green. Critical angle for green, or we can say for longer wavelength which are yellow, orange, red, their critical angle will be greater than the incident angle. So from here we can also say that for longer wavelength which are our yellow, orange and red, their critical angle will be greater than incident angle. Therefore they will refract rather into the air and emerge. Therefore they will refract into air and emerge. So it means wavelength which are shorter, that is our blue, indigo, violet, the critical angle will be less than incident angle. Their critical angle will be less than incident angle. So because of this, they will totally internally reflected. And we can also, you can say, explain same thing by using the refractive, you can say refractive index. So we know that for our VIB VIB GYOR. In this way, the refractive index decreases. Okay. And we know that the sine of critical angle is equal to 1 upon mu. So therefore, as mu increases, C decreases. So based on same conclusion, we can say that the lights that will be coming out will be our yellow, orange and red. Yellow, orange and red. So option number A is correct. Option A is correct. Next question. And it was also asked in 2004. It states that in Young's double slit experiment, two wavelengths 500 nanometer and 7 nanometer were used. What's the minimum distance from the central maxima where their maximum as coincide again? Taking D as this, the sample have their symbols have their usual meaning. So we have to find out the point where the maximum their maximum is going to coincide again. Okay. And in this case, we are going to use the same formula, and we have given two wavelengths. So we have our lambda 1, that is our 500 nanometer, and we have our lambda 2, that is our 700 nanometer. And we are also given capital D and small d ratio is 10 to the power 3. Okay. And we have to, first of all, you can say, look for the condition of a maxima. So you can say condition for maxima, and we assume, let you can say n1th maxima for lambda 1 coincide with n2th maxima for lambda 2. So based on this, we can write that our n1 multiplied by lambda 1 will be equal to n2 multiplied by lambda 2. And we can just find out the ratio, that the ratio of our n1 upon n2 will be equal to lambda 2 upon lambda 1. So we have our 700 divided by 500, 10 to the power minus 9 and 10 to the power minus 9. This gives a ratio of 7 upon 5. So therefore, we have that n1 upon n2 is equal to 7 upon 5. From here, we can say that the 7th maxima for lambda 1 coincide with 5th maxima for lambda 2. And we can just, you can say, make the, in proportion, we can also say that 14th maxima for lambda 1 coincide with 10th maxima for lambda 2. Okay. And the minimum integral value of n1 is 4. So you can say the minimum integral value for n1 is 7, not 4, sorry, 7. So based on this, we are going to find out the minimum distance from the central maxima. Minimum distance from central maxima, and that is governed by the formula that the y is equal to over n1 lambda 1 d upon small d, and we know all the formulas, rather you can say values. N1 is our 7, lambda 1 is our 500 into 10 to the power minus 9, and we are already given the ratio of d upon small d, that is our 10 raised power 3. So let me put here 1, or we can just delete it. And this gives us that the y will be equal to 3.5 millimeter. Yeah. We come to the next question. It was also asked in the year 2004, and it states that an object is approaching a thin convex lens of focal length 0.3 meter with a speed of 0.0 to 1 meter per second. Find the magnitude of the rates of change of position and lateral magnification of the image when the object is at a distance of 0.4 meter from the lens. So here the object is moving towards the thin convex lens. And here we are going to use those two simple formulas, but later on we are going to change them with respect to the speed. So first formula we are going to use is our 1 upon v minus 1 upon u is equal to 1 upon f. We substitute the values, so we get 1 upon v minus, and this comes as minus of 0.4 is equal to focal length given as 0.3, and this gives us that our image, that is our v, is at a distance of 1.2 meters, and these are the fixed position of image as well as the object. Now we want that our image is having a velocity. So we know that the image is, or we can say we have to find rather. So you can say that we want to find the velocity, image velocity, the image velocity. So therefore we are going to differentiate this equation. Let us put this as equation number 1. So we get this as minus 1 upon v square dv upon dt. This comes as 1 upon u square, and du upon dt is equal to 0, because the focal length, you can say, is constant irrespective of the time. It's not going to change. So you can say that focal length, here represented as f, is constant. So therefore we need to find out the dv by dt. So we can write that dv by dt will be equal to, this will become minus minus plus, this will be v upon u whole square and du by dt, and we already know the values. Our v is our, just we found out 1.2, and u is our minus 0.4 and its whole square, and du by dt is given as rate of change of the velocity for the object is given as 0.01. So this gives us that our dv by dt will be our 0.09 meter per second. Next we have to find out the magnification also, and we know the magnification, that is m is equal to minus v upon u. So we differentiate it with respect to time, that is dm by dt. So we can use the formula. This will be u square giving us u as it is, dv by dt, minus v as it is, du by dt, and we already know all the values. So we substitute it, and u is our minus 0.4, and dv by dt we just found is 0.09, minus v is our 1.2, and we have our du by dt is our 0.01, and this comes as minus 0.4 meters. So if we solve this, this will be coming close to minus 0.048 divided by 0.16. So we get rate of change of magnification will be equal to minus 0.3. So these are the two things which we are required to find out. Next question. It was also asked in the year 2004, and it states that figure shows a irregular block of material of refractive index 2. I think it has to be square root of 2 rather. Square root of 2. A ray of light strikes the face AB as shown in the figure. After refraction, it is incident on the spherical surface CD of radius of curvature 0.4 meter and enters a medium of refractive index 1.5414 to meet PQ at E. Find the distance OE up to 2 places of decimal. So we are given this figure, and we are consisting of here 3, you can say, refractive indexes. One is our air, which is mu equal to 1. Another one is our irregular block, refractive index square root of 2. And finally, that is our 1.514. And it says that the incident ray after refraction through the surface CD, it enters medium PQ and meets at E. Okay. So it is going to meet somewhere here. We can say approximately like this. So we have to find out the distance OE. Okay, so we have to find out this distance. So first of all, let's find out what will be the angle of refraction at surface AB. Okay. So for that, we can just draw an approximate figure. So we have a surface AB. This is A and this is B. And we are having, you can say, a normal to the surface like this, and light is incident in this way, and angle is given as 45 degree, and this AB is inclined at an angle of 60 degree, and the refractive index here is of a mu1, that is equal to, sorry, it is mu is given as 1, and here the glass is mu is square root of 2, which is obviously greater than 1. Okay, so it will try to bend toward the normal, something like this. So say it is going to bend towards the normal in this way, and let us find out what will be this angle. And we can use, let us call this as our R, and this is incident angle, that is our 45 degree. So therefore we can use that, let us call this as point P. P is already there. Let us call this as point as R. So we can say at point R, we call this as mu2 and this as mu1. So we can write that our mu2 upon mu1 is equal to sine of I and divided by sine of R. Mu2 is our square root of 2, mu1 is 1, and we have sine of 45 divided by sine of R. So we get from here that sine of R will be equal to, this is sine of 45 divided by square root of 2. Sine of 45 is 1 by 2, 1 by square root 2. So this comes 1 upon square root of 2. Multiply 1 by square root of 2. This will be 1 by 2. Giving us that our R will be equal to 30 degree. So we got that our R is our 30 degree. And if R is our 30 degree, then okay, now if R is a 30 degree, then let's find out what will be the angle of this ray, refracted ray. This is our R, and let us call this as R prime. So we are going to find out the angle between R and R prime and the surface face AB. So let us draw once again the face AB, and we have a normal, and this ray is making an angle of 30 degree, and we also have this angle as our 60 degree. Okay. So this entire angle will be of 90 degree, one second. Yeah, on the bottom side rather. So you can say that this entire angle will be of 90 degree. So therefore we are going to get this angle will be of 60 degree. So therefore we can say our R and R prime will be parallel to AD, because this is our face AD. You can say that angle BR R prime is equal to 60 degree. Therefore we can say our R prime is parallel to AD. If it is parallel to AD, then we can also say, because there is axis which is a PQ. So this is, let me write it here. So we can say our R prime is parallel to, not equal to, but parallel to AD, and it is also parallel to PQ, because PQ is somewhere here. This is a P and this is a Q. So therefore, for the face, the other face, curved surface is our CD. You can say for the face CD, so this is our face CD. And the line or light ray will be coming with this axis PQ, and light ray will be incident on this face, will be coming as parallel like this. And if it is parallel, so this is our, you can say R, and let us call this our R prime. So for the face CD, we are going to have that our incident ray parallel to PQ, which gives us that the object will be at infinity, and we have to find out the V, and we already know the radius of curvature is our 0.4 meters. And refraction is, this is our, this we have taken already, mu2. So with this is our mu2, and let us call this as our mu3. So therefore we can write and mu3 is obviously greater than mu2. So mu3 is denser and mu2 is our rarer part. So it is going to bend in this way and meet somewhere here, and this point is our E. So we have our O and this is our E and this is our Q. So we have to find out OE, or we can say position of the image from the point O. So we simply substitute all the values in the formula, and we have this as our mu2 divided by U, plus we have this as mu3 divided by V is equal to mu2 minus mu3. Oh, I wrote it wrong. So I have here image is at my mu3 upon V minus mu2 upon U is equal to mu3 minus mu2 upon R. Mu3 is our 1.514 divided by V minus mu2 we already know, but that is not required because U is our infinity. This comes as 1.514 minus 1.414 because that is square root of 2, and this is our 0.4. So we get that our V is equal to 6.056 meters, and this is nothing but our OE, which we are supposed to find out. And so I think this, yeah, so this completes all the questions which were asked in the year 2004. Thank you.